Today I want to talk about function types. And we all know what function types are. And we've actually already talked about functions a lot, right? So what is so particular about function types that I have to have a special lecture about it? Well, functions are separate from types so far, right? So far we've worked with this model in which types are objects in our category, right? And morphisms are functions. Pure functions are morphisms. Types are objects, right? So functions are not on the same footing as types, right? But it so happens that, if you are working in the category of set, which is like the approximation of what we do in programming, then actually, you think about it. You have object A and object B, right? Functions between A and B, they form a set, right? They actually form a home set. So that's a home set. And a home set is, as the name suggests, is a set. So if these guys are sets, the types are sets, then this is a set too. So there is actually a set here, let's call it A arrow B, that corresponds to this home set. Right? So this is sort of like a self-referential thing about this particular category of sets. That a home set, which is a set of morphisms between two objects, actually is also an object in this category, right? Because it's a set. But that's not true in general for any other category. That's not true, right? And in particular, if you think that the type system in Haskell is actually category Hask rather than just set, right? Because it has these never-ending computations as part of every type, the bottoms, right? Then in Hask, morphisms and types are kind of different, right? So you don't have this. So this is called an external. In an arbitrary category, we don't have this object. What we have is the home set being an external thing. A home set being actually a member of set, a different category. That's why it's called an external home set, right? What we would like to have is an internal home set. An internal home set would be an object like this, right, in a category that corresponds to the set of morphisms between two objects, A and B, right? Somehow represents this set of morphisms. And it's possible to define it, maybe not in an arbitrary category, but in many categories, it's possible to define this object. And of course, just like we are defining, so this would be an object that corresponds to two objects A and B, that's functions between A and B. So just like we were defining product, coproduct, and all these things, right, inside a category, the same applies to constructing this object, the function object. So we can use a universal construction to construct a function object. Okay? So how would we go about this universal construction for a function object? Well, we have to first, right? You remember the three steps in every universal construction. First, we define a pattern. Then we define ranking between matches, right? And finally, we say the best match is our guy, right? So let's start with the pattern. So this pattern for a function object obviously must involve these two types, the argument type and the return type of the function, right? So we have two objects, A and B. Okay, good. And the third part of this will be this object that we want to be our candidate for the function object. Okay, so let's call this object, let's say Z. Okay, arbitrary name. So we have three objects, but we have to have some kind of connection between these objects, right? What would define for us the action of a function on an argument that produces a result, right? We have to like find a morphism maybe between some of these objects that would represent this idea, right? But it's a relation between three objects now, right? There is the argument, I call it A, right? Argument type, there is the return type, and there's the function type. So three things, how to draw an arrow between these three things, right? We would like to have to say like, okay, we take a function and an argument, and that produces a result, right? So we would like to put an arrow between these two objects and the third object. We can't do it in a category, right? All these arrows are just singularities, right? So let's think about how would we do it in set, or in set we would say, okay, let's pick an element of this set, right? Which will be our function, right? Let's pick an element of this set that would be the argument, and form a pair. Function and its argument. And this pair, function and argument, can be mapped to the result, which is an element of B. Okay? So that gives us the idea. Pairing corresponds, in sets, corresponds to taking a Cartesian product of these two guys. Right? Okay, so a Cartesian product, we can generalize it to an arbitrary category, well, not arbitrary category, to a category in which we have products. So we can take Cartesian product, generalize it to a categorical product, and say, okay, so we have a product of, so let me draw this as more, in a more kind of productive way. So this is a Z, this is an A, and a product is like the square of whose one side is A, one side is Z. So this is our product Z cross A. And it's an object in the category, right? So if we have an object in a category, then we can have a morphism from this object to this object. Okay? So that's the pattern that we are looking at. But notice that in order to define this pattern, we have to have a product in our category. And that's a very important thing. In order to define a function object in a category, you have to first define a product. If the category doesn't have products, then we cannot perform this construction. And you will see later that actually it makes more sense when you think about function object as algebraically as an exponential, because an exponential is like a iterated product, right? So if you don't have a product, how can you have an exponential? So that's the idea behind it. Okay, so this is our pattern. And often this function is in the end, this function will be called the eval function, the evaluation. Give me a function, give me an argument, and I'll give you a result. That morphism is called evaluating a function and an argument, right? So that's the first thing to do in defining a universal construction. The next thing is ranking, right? So suppose that we have, I'm going to redraw this, right? So this is our A, this is our Z, this is our A cross Z. Now suppose that we have another candidate, Z prime, and we want to compare these two. So we will say that Z is better than Z prime, and sort of natural thing, right? I mean, we usually say something is better than something else if there is a morphism between them, right? So we'll say it's better than Z prime if there is, and again, we always say unique morphism, right? So if there is a unique morphism, let's call it H, from Z prime to Z. Okay? From Z prime to Z, there's a unique morphism. Okay, that's not good enough, right? Because we also have this function here, G, right? So this pattern consists of A, B, Z, and the morphism G. This pattern that's competing with this one consists of Z prime. Here will be A, this could be Z prime cross A. This is Z cross A. Okay. And the morphism is called G prime. Right? So we have two matches for this pattern. One with Z and G, and the other with Z prime and G prime. Now we are saying, okay, there is a unique function H from Z prime to Z, but we have to have some kind of connection between G and G prime, right? We have to be able to like factorize, like we did with product and coproduct. We have to factorize this arrow through this arrow, right? So like every evaluation, every candidate for evaluation should be able to, we should be able to factorize it through this good evaluation, right? Okay, but, so we would like to have something here, right? We would like to have an arrow here, so we could say that G prime is G after this arrow. That would give us like a triangle here, right? We could say this, that if this diagram commutes, then Z prime, then Z is better than Z prime, right? But what is this arrow? We have an arrow H here between these guys that we started with, but what is this arrow? Well, and this is why I was waiting with this. Why didn't I just introduce, product, coproduct, function type all at once? Because I had to wait for this lecture because I needed the functoriality of the product, right? So now let's remember this. A product is a bifunctor. What does it mean? It means that it not only takes two objects and produces a third object, right? But it also takes two morphisms and produces a third morphism, which is the product of these two morphisms, right? So now we have two products, two product objects, right? We can form a morphism between them, which is a product of two morphisms. So what kind of product would we have here? Well, from Z prime to Z, that's the H, right? So we have to take H fit it somewhere here. So it's H acting on the first component of the product. And what's acting on the second component of the product? ID, right? So this morphism here is a product of two morphisms. It's a lifting of a pair of morphisms. One is H, one is ID, right? And it maps Z prime cross A into Z cross A. Okay? And that's what we needed. We needed that. We needed this bifactoriality so that we know that it's possible to actually map products. It's not totally non-trivial, you know, that if you have products that you can map them, right? That you can form this kind of product of morphisms. But now we know we can. Okay? So let me summarize this. We established the ranking between candidates, and we say that Z is better, well, actually Z with G is better than Z prime with G prime, only if there is a unique morphism, H, from Z prime to Z, such that this diagram commutes. Let me write it down, the commutation of this diagram, right? So this is, it says that G prime is the same as G after Z cross, H cross ID. Okay? That's the formula. But of course everybody remembers stuff, diagrams, right? And you derive the formula by looking at the diagram. So the composition of these two morphisms is equal to this morphism. That's our commutation condition. And finally, right, the third part of universal construction is picking the winner, the best object that is the function object, right? And that's the one that has, so maybe I'll just write this on top of this. So this will be, I will call this object A double arrow B, temporarily, okay? So this is the function object, this is our universal object, right? If we have this object A arrow B, the function object, I have to replace A arrow B here. I will call this G eval, okay? So this is my winner. I'm calling this function object A arrow B. This is just a name for this object, okay? Just a name. It's just a compound name, right? I form a product with A, and I have a function that I will now call eval, right? And this is the best one, meaning that for any other Z, right? For any other candidate, and now this can be absolutely any other candidate Z that has this function G from Z cross A to B, right? So for any pair like this, Z and G, there is a unique morphism H that maps Z to A arrow B. Okay? Such that this triangle commutes. So that's very similar to how we define product and coproduct, right? We just find the best match for our pattern and we call it the winner. Okay?
Quick question.
Mm-hmm.
And then the function object is said to exist only if you can always find that H.
Yes.
So if you have an imposter but you don't have that H, then the function object doesn't exist.
Right, right. So a function object only exists when for every possible pair Z and G, like this, there is a unique morphism H. Only then you can say it exists, right? Otherwise, we just say, well, there is no function of G. Yes?
Also, this diagram doesn't show the arrows that make sure A to B cross A is a pair, but like they are there, right? Like A to B cross A does satisfy the conditions of a product. There are arrows.
Like defining the product.
Yeah.
Okay. No, I'm not showing that because
Okay,
I'm already, you know, I already know how to do products, you know, so obviously this is obtained through some other universal construction of the product. Right. But I don't have to show it anymore because we've been through this, right? So you know how to create this product. And the assumption is that we have a product for every, so we have like a Cartesian category. So we can create these products for every pair of objects. Okay, now I want you to look at this diagram slightly differently. Okay? Because we can say, you know, this sort of corresponds to our understanding this function G, right? This morphism G, that corresponds to our understanding of what it means to have a function of two arguments, right? There's a slightly different interpretation of this diagram. So G is a function of Z and A, right? This is why I picked Z rather than, you know, calling it F or just, you know, a function of two arguments in most languages, we sort of understand it as a function from a pair, right? Or function of multiple arguments, a function from tuple, right? And this is even the syntax of most imperative languages suggests this, right? When you write, you know, you write f of x, y, z, well, that looks like a tuple, right? So if a function of multiple arguments is really a function on a tuple. So this sort of generalizes this idea that instead of a tuple here we have a product, you know, a categorical product, but it's sort of like we can think of G as a function of two arguments, right? But now we are seeing something, you know, that the function of two arguments is equivalent to a single function that takes an argument and returns the function type. See that? Okay? Because there is a one-to-one correspondence between every G and H, right? I said part of the universal construction is that for every G like this, there's a unique H. So you have a mapping from G to H, right? Now, if you have an H, then obviously you can create a G. How? Well, use this formula, right? Well, okay, this formula rewritten for this diagram says eval here, right? So this G is equal eval after H cross ID. So given H, I can create a G, I can get a G, and given G, I have a unique H. So there is a one-to-one correspondence between these G's and A's. Okay? So I have a one-to-one correspondence, the equivalence of two ways of thinking. One way of thinking, I have a function of two arguments as a function that takes a product, right? And the other one, it's a function of one argument, but it produces a function. Okay? And that's called currying. So currying is built into this universal construction. Right? So h, you know, is a function that takes a z and produces a function from a to b, right? Now, I'm starting to use single arrows here, okay? Because in Haskell, right, this function object is really represented by an arrow, right? When we take two types and put an arrow between them, right? That produces a function type. That's this kind of type, you know, like this. And G was of the type Z cross A, or in Haskell, Z comma A to B. And these two are equivalent. And in Haskell, this is sort of, well, first of all, in Haskell, this is sort of trivial. And you can actually write two functions, curry and uncurry, that convert functions from one style to another style, right? We usually write functions in this style, but sometimes we want to use this style as well. So the function curry takes a function of this style. So it takes, well, let me rename things a little bit. So A, B, C, and produces a function A, B, C, right? So take a function of two arguments as a pair and turn it into a function that's curried, meaning a function returning a function, right? So how would we implement this? So let's call this function f here, right? And we want to produce a function, okay? So we take this function and we want to produce another function. How do we produce functions in Haskell? We use lambdas, right? So we say lambda takes an argument a. Well, I'll call the value a as the same as type a, right? And now I want to produce a function that takes a b and returns a c, okay? So I'll say lambda b, okay? And now I want to produce a c from, but I have a and b at my disposal, right? So I can just call f with a pair ab. Okay? So my function takes a pair, right? And now I have two elements of this pair, a and b. I can form a pair, and I can call f with this pair, right? And that in Haskell is a function of one argument, but it takes an argument which is a pair. Okay. And there is a corresponding uncurry. That does the opposite, right? So it takes a function from a to b, c, and produces a function from a comma b to c. Okay? I'm putting lots of redundant parentheses, and in a moment I'll explain that I don't really need them. So uncurry takes a function, let's call it f again, right? And it produces a function of two arguments, a and b, right? Of a pair, a function that takes a pair. I can write it in this form, right? So it's a function that takes a pair ab, right? And what? Calls f with a and b. Well, I'll put parentheses here, okay? So that everything is clear. I don't need these parentheses, but I will put them. So what it means is that here I have a function that takes a single argument and produces a function, right? So I'm applying this function to a, and the result is a function that requires a b. So I'm calling it with a b, and finally I get a c, right? And that's exactly what I want. Now about parentheses, okay? So the things are done in Haskell in such a way that, that the arrows associate nicely. So the arrows here, they associate to the right. Therefore, I don't need these parentheses. And you will see, you know, functions of 2 arguments in Haskell written in this way. Like all these guys are arguments and the last one is the return value, right? And that just means can be interpreted as, you know, a function of 2 arguments, right? Or a function that returns a function. So I can put these parentheses, I don't have to, I can, right? Because of associativity. So unlike with other multiplications and products, coproducts and so on, this thing is not associative in the sense of a monoid, right? It associates always to the right. It's not that you can associate it any way and it's the same thing. No, it always associates to the right. Whereas here, I don't need these parentheses either, because function call associates to the left. So if I say FAB, it means I'm calling f with a, produce function, and then call it with b, right? But normally we don't think of it this way. We're just thinking we're calling f with 2 arguments. But it's the same thing, right? So currying is built into Haskell. It's intrinsic to Haskell. And any function of more than 1 argument is automatically curryable. You know, we don't need to do anything special, right? Like in other languages, you have to have special. Well, you have to have curry and uncurry as special. Like in C++, you would have templates that do this for you, and in Scala, right? In Scala, I think you have 2 options. Either you define your function with multiple sets of parentheses, then you can curry it, or you apply some higher order function to curry and uncurry. But in Haskell, this is automatic. No problem. Okay. So, this is how we do function object. This is how we do currying. Now, in category theory, very often people don't call this a function object. They actually call it an exponential. And it really makes sense if you think about it. Why it's called an exponential. So a function from a to b would be called an exponential b to the power of a. Okay? Argument goes on top, result goes in the bottom. Okay? So it's from a to b. You have to remember. It's like, maybe it's not totally natural. This is the argument and this is the return type. Well, let's think about examples. So for instance, if we have a function that goes from bool to int, right? I said before that a function from bool to int is really 2 integers, right? So it's really a pair of integers. A single function from bool to int is just a pair of integers. One for false, one for true. Okay. If you want to talk about the type of functions from bool to int, then it's a set of all possible functions from bool to int, right? It's a set. So all possible functions from bool to int, well, they are just all possible pairs of ints. Okay? So this is really a Cartesian product of ints, right? So you can write it as int cross int in categorical way, right? Or you can even write it as int square, right? Okay, and remember that we had this funny notation that 1 corresponded to a unit type, right? 2 corresponded to Boolean type, right? So I could have written this as int to the power of Boolean. Okay? So in this sense, this is really an exponential. Function types are exponentials, and as long as the types here are like finite sets, like Boolean or color, unit, if they have character, the number of functions from A to B is really b to the power of A. If you look at all possible combinations, how many different combinations you can form, you find out that this is really b to the power of A. So by counting the number of possible functions, you get this, counting argument. And also, this shows you the connection between product and function type and exponential, right? This is why, an iterated product gives you an exponential. So now, what we do want for programming is a category in which we have exponentials or function types, whatever you call it, right? We definitely want products, right? Because if we want exponentials, we want products, right? So there is a special kinds of categories called Cartesian closed categories that are useful in programming. And these are the categories, well, you know what Cartesian category is. One that has products for every pair of objects. Closed means that it has all exponentials as well. For every pair of objects, A and B, it has an exponential a to the power of b, right? And also it has a terminal object. Why terminal object? Because the terminal object is really, if you think about it, the terminal object is like this 0th power of an object. It's like the first power of an object is the object itself. Second power of the object is the product A cross A, right? Then we can have these exponentials, right? But the 0th power is the terminal object. Is it really? Okay, I'll have to show you this, right? You don't believe me, and you shouldn't, right? Okay, so Cartesian closed category. You'll probably hear this spoken many times. Cartesian closed categories, or CCCs. CCC, Cartesian closed category. That's a category that has products, that has exponentials, and it has terminal objects, right? We actually want a little bit more in programming, right? We also want coproducts, and we want initial object, right? So something that has not only Cartesian products but also coproducts is called bicartesian closed category, BCCC. Okay, bicartesian closed category. Has products, has coproducts, has all the exponentials, has an initial object and a terminal object. And from now on, we'll be, when we talk about programming, we'll be actually sitting in a bicartesian closed category. And in a bicartesian closed category, we can do all our beautiful algebra of types, right? So we've seen so far, the algebra using products, coproducts, initial objects and terminal objects, right? We saw that they formed, first of all, products form a monoid, coproducts form another monoid, but we can even combine them together and they give you this semi-ring, right, or rig, right? And now we are adding exponentials. So with exponentials, we can do more algebra. For instance, what's a to the power of 0? One.
Yes.
Makes you great, doesn't it?
Okay, so we all know this, right? But is it true for types? Okay, now we can interpret this. So what is this? Remember, this is the argument, this is the return type. So this is a function from, what is 0? That's our initial object, right? So that's our void. Okay, so void. So it's a function from void to a. Okay? The right hand side is 1. 1 is the terminal object, that's the unit type. Okay? Unit type. Are these two types equivalent? Well, what would that mean? A unit type is a type that has only one element. Okay? So if this is a singleton as well, then we are done. Okay? So first of all, is there a function from void to a? And how many are there? Well, we've seen this function. It's called absurd, right? This function is called absurd. It takes a void and produces an a. And this is the tricky function, right? It's like, hey, give me an element of void, I'll give you anything, right? So there is a function like this, and it's only one function like this, right? So indeed, a to the power of 0 is 1 in types. Okay? Cool. What about 1 to the power of a? Arbitrary a. Like you take 1 and you multiply it by itself many times, right? Well, you still get a 1, right? Okay, well, what does it mean? So this is a function that takes an argument of type A and produces a unit, right? And I'm saying that this is the same as unit. Okay? So there is only one function like this. It maps all elements of A into this unit element, right? There's only one. This is the one collapsing. This is a const function that turns everything into one single value, right? So this is also true. Okay. And let's do one more before a break. A to the power of 1, right? And that's obviously A, right? You take A. So that's what I meant by saying that, you know, the first power of an object is the object itself. But it also has this meaning that a function from unit to A is isomorphic to type A, right? And remember what this is? This function that from unit to A, unit is a singleton, right? This function from unit to A, it's a function that picks one element from A. So there are as many such functions as there are elements in A. There is a one-to-one correspondence between this. I call it generalized element, but really people say that it's called a global element. It's a more mathematical name, right? So this is called a global element. this morphism in general is called a global element. So global element is the same. Okay. So let's take a break now, and we'll continue.